Chapter 2, Lecture 2. So in this particular lecture, we'll take a look at the first law of thermodynamics, which is, as the slide says, it's a good basis for studying the relationships among the various forms of energy and the energy interactions. So the first law is basically a conservation of energy. It says that energy can neither be created nor destroyed. It can only change forms. So here, for example, if you have as an example you may be familiar with from physics, is if you have a rock on top of a hill, you have a certain amount of stored potential energy. In this case, let's say it's 10 kilojoules. Well, if the rock falls off the cliff, you can convert that potential energy into kinetic energy as the rock falls. So at any point along its fall, it has a certain amount of potential and kinetic energy, but the sum of those two always adds up to what the total energy of the system is. Mechanisms of energy transfer. So let's say we have our system that's contained inside what's known as the control volume. The little pink dashed line here is our system boundary. Everything inside is our system, which has a certain amount of volume. That's what we call the control volume. Everything outside is the environment. So mass can pass through the boundary into the control volume. Mass can leave the system through the boundary. You can also have work being done on the system, or the system doing work on the environment. That's W. You can have heat flow into the system across the boundary, or heat flow out of the system across the boundary. But the change in energy of the system inside is equal to the difference between how much energy comes in and how much energy comes out. Now, this left-hand side of this equation, En minus E out, can be broken into three main categories like we've shown here. You have the Q terms coming in and out, the difference. You have the work differential, work in minus work out, and you have the energy of the mass coming in minus the energy of the mass coming out. Because remember, a fluid, moving fluid, carries a certain amount of energy just due to its motion. So that defines how the change in energy inside here occurs through these three processes: heat change, work change, and mass flow change. So how does the energy of the system involve? So we've taken a look at the left-hand side of this equation. That's literally determined by these three terms: our heat term, our work term, and our mass flow term. The right-hand side, internal to the system, can change in, again, three ways. You can have a change in internal energy, delta U. You can have a change in kinetic energy, and you can have a change in potential energy. Now, if a system is stationary, these kinetic energy term and this potential energy term are both zero. In a lot of our cases, some of our cases, one or both of these terms will be zero. So let's look at an example. Let's say we have our system is the pink area here. We have the boundary around. We have heat flow, 15 kilojoules of heat coming in across the boundary into our system. We have 3 kilojoules coming out of the system, and we have 6 kilojoules of work due to shaft work being done on the system. So how much did our energy of our system change? Well, we can just plug it in our formula. The change in energy of the system is equal to the difference in the heat flow, 15 kilojoules minus 3 kilojoules, plus the difference in work. Well, there's 6 kilojoules being done on the system. The system doesn't do any work, so that's the work out's zero. There's no mass flow change, so both of those terms are zero. So if you add these terms up, you get 18 kilojoules. That's how much this energy of the system has changed. Now, that energy of the system can change several things. It can increase the kinetic energy of the system, it can increase the potential energy of the system, or it can increase the internal energy of the system. This kind of case where you have a system isolated to a box, obviously the potential energy is not going to change. You're going to increase the kinetic energy, or you're going to increase the internal energy. Let's take a look at an example. So a rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is 800 kilojoules. During the cooling process, the fluid loses 500 kilojoules of heat, and the paddle wheel does 100 kilojoules of work on the fluid. Determine the final internal energy of the fluid. Neglect the energy stored in the paddle wheel. So we can start with our basic equation I've highlighted here. Let's calculate how much energy comes in and out of the system. So Q in is 0, Q out is 500 kilojoules, the work in is 100 kilojoules, the work out is 0, and there's no mass flow in or out of the system. So the E in minus E out turns out to be minus 400 kilojoules. So let's calculate how much change in energy of the system. So the change in energy of the system is given by the change in internal energy plus the change in potential energy plus the change in kinetic energy. Now, both the potential energy terms and the kinetic energy terms are 0 because they're not, nowhere in the problem does it say the fluid changes elevation or it speeds up. So therefore, those terms are 0, and change in energy of the system is just equal to the change in internal energy, which is U final minus U initial. Now, E in minus E out has to be equal to E system, so U2 minus U1 has to be equal to minus 400 kilojoules. And since we know what U1 is, that's the initial internal energy, we can solve for the final internal energy. Turns out to be 400 kilojoules. Efficiency is one of the most frequently used terms in thermodynamics. It indicates how well an energy conversion process is accomplished. The basic definition is that performance is equal to desired output over required input. And you can often see these efficiencies, for example, on water heaters. If you go look at water heaters, that's exactly what it's telling you. It's the ratio of the energy delivered to the house by the hot water to how much energy is supplied to the hot water. How much energy does it take to heat up the water, basically? That's the energy input. The energy output is how much energy does it actually deliver to your house in hot water. If you have a combustion process, there's another way you can define efficiency. It's given by Q over the heating value of the fluid. And there's two types of heating values. There's a lower heating value and there's a higher heating value. The difference is basically equal to the heat of vaporization. So this energy efficiency of combustion, they calculate it a different way depending on if they use the LHV or the HHV. They're pretty close, but there's a little bit of difference. So let's take a look at the power plant efficiency. So here we have a mock-up of a power plant. We have a combustion chamber where the fuel is burned. We have some thermal systems that carry the hot fluids through the pipes. We have a generator that's going to turn the mechanical energy into the electrical energy. So how do we calculate the efficiency of this overall plant? Well, it's a product of the efficiency of combustion for the combustion chambers, the efficiency of the thermal system, which is the intake and turbine itself and the steam flowing through it, etc. Then there's the efficiency of the generator itself. So it's overall it's a product of these three different efficiencies. So it's how much input power divided over the high heating value times the net flow rate. This is an equation the book puts out. So let's look at an example of efficiency. Here we have a cost of cooking with electric or gas. It's a simple problem. He wants us to compare the two. He says the efficiency of open burners is 73% for electric units, 38% for gas units. If we have a 2 kilowatt electric burner at a location where the cost of electricity and natural gas are 9 cents a kilowatt hour and 55 cents a therm, respectively. So this was for the electrical gas range, and this is for the natural gas range. Determine the rate of energy consumption by the burner and the heat cost of utilized energy for both electric and gas burners. So we can calculate the The heat flow rate is the energy input times the efficiency. Uh, so here we have for the electric, it's 2 kilowatts times 0.73 or 1.46 kilowatts. The cost of utilized energy is the cost of input divided by the efficiency. So it's 9 cents a kilowatt hour divided by 0.73 or 0.123 dollars per kilowatt hour. We can do the same thing for the gas. Q dot is 1.46 kilowatts divided by 0.38 or 3.84 kilowatts. And now you have to have some conversions. You have to know, for example, what's a therm? A therm is a 29.3 kilowatt hours. So we can find the cost of utilized energy. It's 55 cents divided by 29.3 kilowatts divided by 0.38 or 0.049 kilowatt hour. So comparing the two, you can see the cost of the gas is less than half the cost of the electricity. Therefore, even though electric appliances are typically higher efficiency, cooking with electric burner will cost more than twice as much compared to a gas burner. This is why, if you really want to save money on appliances, always go for the gas ones. It's not wise to try to use electricity to heat. You can also calculate some efficiencies of other mechanical and electrical devices. The book gives formulas for efficiency of mechanical efficiency, efficiency of a pump, efficiency of a turbine. So you can look these terms up if we need them, and just look up these formulas. You'll have a formula sheet available for you to be able to calculate these. He gives a simple example where he has let's say we have a 50-watt fan here, and we measure the flow rate through it. M dot is 0.5 kilograms per second. The change in velocity across the fan is 12 meters per second. Obviously, we're not going to change elevation, and the pressure is approximately the same on each side. So here we can sort of calculate what the efficiency is. It's the change in kinetic energy over how much energy it put into this thing. So it's 50 watts on the bottom. That's what power supplied it, over the change in kinetic energy. So we know what the flow rate is. We know what the velocity is. We can calculate that. So we get the efficiency of the fan is about 0.72. You can also calculate the efficiencies of motors, generators. You could have a pump motor combination or a turbine generator combination. So these formulas are pretty generic. And there's if you need one, you can simply look them up on the exam, or in the real world, you can look them up as well, of course. So let's look at an example here. You have a turbine and a generator. The turbine's powering the generator. The turbine has an efficiency of 0.75. The generator has an efficiency of 0.97. So the combination together has an efficiency is the product of the two, 0.73. And this sort of makes sense. I mean, even though the generator is much more efficient than the turbine, the combination together has to meet somewhere toward the lowest common denominator. You're going to be the product of the two, much lower, 0.73. So here's an example out of the textbook. This is maybe similar to the kind of homework problem, test problem you might see. Electric power is to be generated by installing a hydraulic turbine generator at a site 70 meters below the free surface of a large water reservoir. This reservoir can supply water at a rate of 1,500 kilograms per second. If the mechanical power output of the turbine is 800 kilowatts and electric power generation is 750 kilowatts, determine the turbine's efficiency and the combined turbine generator efficiency of this plant. Neglect losses in the pipes. So here's a little schematic we have. Obviously, it's going to be a conversion of potential energy to kinetic energy. We have a generator and a turbine, so as the water flows through the turbine, It turns the turbine blades, which turns the generator and makes electricity. Um, so you can calculate the change in potential energy. It's 70 meters, so it's this G times Z. Uh, and we're going to convert this, again, this is our conversion factor, to convert this to energy per unit mass. Then this rate of mechanical energy supplied to the turbine is simply is just m dot times this small e that we got from up here. So we know what the flow rate is. It's 1,500 kilograms per second. We can plug in our 0.67, and we get 1,031 kilowatts. So now it's a simple matter to calculate our efficiencies. We just calculated the denominators, how much energy we had to put into the thing. We know, for example, for the first one, it's 750 kilowatts out, so it's a 72.7 efficiency. And for the turbine itself, it's 800 kilowatts divided by 1,031 kilowatts, or 77.6%. So therefore, we can conclude that the reservoir supplies the 1,031 kilowatts of mechanical energy to the turbine, which converts 800 kilowatts of it to shaft work that drives the generator, which generates 750 kilowatts of electrical power.